All right, Dr. Matthew J. Trom here. I'm going to give you a brief overview on motor controls for our motor control lab. The first thing that you need to know is how a motor works. Obviously, there's a lot more nuance in this, but it's essentially a permanent magnet and an electromagnet. And the electromagnet changes its polarity and then it aligns with the permanent magnet. And then you change the polarity again and it flips over to align with the permanent magnet with the opposite pole. So again, there's a lot more detail to it, but that's essentially what you need to know in order to, diagnose a lot of problems and understand how these things work in the context of Capstone. So there's essentially three types of motors that we deal with in this kind of digital world of mechatronics. So the first is a DC motor. So these are characterized because they typically just have two wires coming off of them, and that provides the power, which is usually just a voltage. Um, Constant voltage, so the motor will turn relative to how much voltage is put across it. So two wires, relatively high RPM, so you can get these to go up to 10, 20, 50, maybe even 100,000 RPM, so they go pretty fast. You control the speed, as I said, by changing the voltage that you put across them. The direction is based on the polarity of the wires. And there's no position feedback, right? So these things can turn all day, but you have no idea in rotational space where the shaft is at any time. The other kind of extreme is a servo motor. And servos have relatively low RPM, so like 50 and below. They are the only type of motor, at least that we deal with here, that has some closed loop position feedback. So you can actually tell a servo where to go in rotational space, and it'll go to that spot, and usually pretty accurately. And so as a result, these have three wires, so two that carry power, and then the third, which carries the position signal to tell the servo where to go. What I will mention is that ability to determine the location is based on um, a potentiometer that's built into the servo. And so servos typically can't run more than 360 degrees, right? So they can't turn around and around and around. They basically have a hard mechanical stop once they turn around once. And then the third type is a stepper motor. Stepper motors are kind of in the middle in terms of RPM. You can run them up to about 200 before they start skipping steps. These are open loop position control, so you can tell them how many steps to move, and you're relatively assured, provided you're not driving the motor in a weird way outside of its specifications, that will actually take that number of steps. These are basically powered by four wires. So each wire energizes and de-energizes a coil, and how that coil energizes and de-energizes affects what direction the shaft goes and how far it goes. So that's kind of the broad brushstroke overview of those three types. Um, with the exception of servos, motors are effectively blind, meaning they don't know where they are in rotational space. And so you can get some information about where it is in space by adding sensors. So you might add something like an encoder that will give you a rotational position. Sometimes those will also give rotational speed. Or you could use things like limit switches to give you like a travel range for a motor, right? So if a motor is turning and then it has a little mechanical nub on the shaft that maybe touches off on like a roller switch like this, closes the switch, that sends a signal to your control board that the motor has reached that point and now it's time to shut off the motor, turn the motor the other way, or something like that. So even though the motors themselves don't have inherent built-in control feedback, you can add extra sensors and extra components to enable that. So here's kind of an internal schematic of a brush DC motor. Like I said, there's essentially a winding. You run current through the winding. It creates a magnetic field, and that magnetic field aligns with a permanent magnet inside the motor. To get the motor to turn, you just switch the polarity of the current running through the wire loop. The magnetic field, electromagnetic field switches direction, and then this will again try to align with the permanent magnets, and that's what causes it to spin. Um, Typically, DC motors are characterized by a so-called motor curve. So I show in here that actually has multiple different parameters. So we've got torque on the x-axis, and we've got several variables, but the important one is speed on the y-axis. And normally these things are analog, right? So you'll just take a battery, you'll attach it to some sort of resistor to allow you to change the voltage across the motor, and then you've got the motor just kind of in this circuit here. And the way that this works is this is a potentiometer, and you'll just change the resistance, and changing the resistance just increases or decreases the voltage that you see on the motor, and that will either increase or decrease the rate of rotation. If I wanted this to go the other way, I would just swap the wires around, and that causes the motor to turn in the other direction. So a lot of times I'll find that students will buy DC motors from like inexpensive vendors who don't provide specifications. And so the way to kind of back out how one of these DC motors is going to perform is to identify two important points. So the first one is the stall torque. So this is the point where you put so much torque on the motor shaft that it basically stops turning, right? So the speed is zero and the torque is maximum. So that's one point. And then the other extreme is the no load speed. So this is you've got nothing, no load on the shaft, no torque on the shaft, and the motor is spinning as fast as it possibly can. So that's the no load speed. So if you have the no load speed and you have the stall torque, if you connect those 2 points by a line, that line is pretty good, a pretty good predictor of how the motor is going to perform. So that's the technique that I always tell students: just test those 2 points and then connect those two lines, and that'll give you a useful motor curve. I also include here the efficiency curve, and usually when motors are designed and put into operation, they're put in operation pretty close to the peak of their maximum efficiency curve. That's just so that they use as little power as possible to achieve whatever rotational and torque metrics are required. But I want to just mention that as well. What I represented on the previous slide was analog motor control. And of course, we live in a digital world. And so we have to somehow trick these DC motors into thinking they're seeing an analog voltage when really all that we can provide is a digital voltage, either 0 volts or 5 volts. And so the way that that's done is through a technique called pulse width modulation, PWM. And if you think of a duty cycle, so just time kind of moving here in the X direction, all we have available to us in the digital world is 0 volts and 5 volts, the low signal and the high signal. And so the way that we'll get these motors to spin at different speeds and in different directions is we'll just vary the amount of time. So we'll send a series of pulses, and we'll vary the amount of time that those pulses last for, right? So if you've got the pulse at 5 volts for 25% of the time, you're running a 25% duty cycle. And these pulses come in so fast that what the motor effectively sees is just the average output voltage, right? So this would be, something like 1.5 volts. This would be 2.5 volts. This would be 3.75 volts. And then if you're running 100% duty cycle, you're not pulsing at all. You're just sending the, full bore 5 volt signal. Then the motor will run at 5 volts. So that pulse width modulation is controlled by something called a motor driver. So you feed power to run the motor into the motor driver. You run the logic of the motor driver off of a 5 volt signal, and the motor driver will do all of the pulse width modulation calculations and signal sending for you. You just need to find an appropriate library, drop that into your code, and say, "Hey, motor driver library, run my motor at this speed and this direction." And the motor driver, if you've programmed the code correctly, will just convert your code into the signal that it sends through pulse width modulation down the wires to the motor. So but it's, I think, good to know kind of the background of what the code and the hardware is doing, especially for purposes of troubleshooting. Okay, so the next type that we'll kind of deep dive into is a servo motor. As I mentioned before, servos are the only types that we typically use in this class that know where they are in rotational space. So it's typically a DC motor geared down pretty significantly. So that's where you get the relatively low speed and high torque. And then the shaft is attached to a potentiometer, and the potentiometer sends a signal back to an onboard control unit, which basically tells the motor to start and stop and which direction to go in based on the control signal that you send the servo to tell it where you want it to go in rotational space. So this is the one of the three types where it actually knows where it is. So how do servos work? As I mentioned before, they have three wires, two for power, one for the command signal. So the way that the command signal works is that the servos have a 20 millisecond duty cycle, right? So they're basically sitting and waiting every 20 milliseconds for a pulse. And what they'll do is measure the distance or the duration of the pulse. And it's sort of like, dots and dashes in Morse code. The length of the pulse tells them where to go in rotational space, right? So a short pulse will tell it to go to zero. A relatively longer pulse will tell it to go to 90 degrees, and an even longer pulse will tell it to go to 180 degrees. So as soon as it receives this signal, it'll start moving in that direction towards where it was told to go. And then when it gets to that spot, it'll stop and wait for another 20 millisecond duty cycle to get another signal to send it to the next location. So just like with motor drivers for DC motors, the pulse control for servo motor location is done on the back end. So it's not something that you need to manually code. All you need to do is find an appropriate servo library and drop it into your code. And you usually just tell the servo library, hey, send my servo to 0 degrees, 180 degrees, 270 degrees, whatever it is. And in the code in the library that will convert your axial location, your command signal, to a pulse length and send the pulse down the control wire of the servo without you having to do anything to manipulate that. So, okay, the third type that we deal with is a stepper motor. I think the easiest way to understand how a stepper motor works is to give you kind of a simplified schematic. So imagine a stepper motor is basically an internal permanent magnet surrounded by coils. And so I've got the A coil here and I've got the B coil here. So in this case, I've just got two coils. And the way that I get the motor to turn is first I energize the A coil. So that sets up a magnetic field that causes this permanent magnet to align with the A coil. And then when I want to take a step, I de-energize the A coil, energize the B coil, and this permanent magnet will now turn so that it aligns with the B coil. And I can actually get it to rotate in any direction that I want and as fast as I want by just changing the energizing and the de-energizing of the A coil and the B coil. So that's kind of the big picture of how they work. Now, normal stepper motors that you buy don't just have like two locations. Typically, they have 200 locations around a 360-degree radius. And so I think that's about 1.6 degrees per step. So each one of these, you can actually see it zoomed in here. Each one of these teeth is very similar to like the B prime B or the AA prime coil. And there's essentially two coils, just like there was before, and they just energize and de-energize. And what's happening is the permanent magnet on the inside is just taking these tiny little steps from one tooth to another tooth to another tooth inside the stepper motor. And so every time you want the stepper motor to step, you just de-energize one coil, you re-energize the other coil, and all of a sudden the stepper motor will just move like one increment over so that its permanent magnet, internal permanent magnet, aligns with the next tooth, the one that you've now energized. So that's effectively how they work. So just like DC motors, you can run a stepper motor with a motor driver, and the motor driver does all the logic for you. So you don't need to like figure out which coil I'm energizing and de-energizing and how fast, and like you don't need to worry about any of that. All of that is handled by the motor driver. Motor drivers do operate on 12 volts because stepper motors need 12 volts. So you have to feed this thing 12 volts, and then it determines across four wires how to send a signal to the stepper motor to get the stepper motor to turn the way that you've commanded it to turn. So remember, there's two coils in the stepper motor. Each coil is energized and de-energized in tandem to get them to turn. And so you would expect two pairs of wires to drive a stepper motor, and that's exactly what we see is four wires, two pairs, four wires that turn the stepper motor. So all that is self-consistent. The signals that you need to send the stepper motor are a signal to step and a signal for what direction you want it to step in. So there's two pins that will feed into your motor driver. One of those pins is the command to step, and the other one is the direction command, whether you want to step clockwise or counterclockwise. And so every time you send a pulse, that causes the motor to take one step. And whether you've got the direction at the high voltage or the low voltage determines whether or not your stepper motor is turning clockwise or counterclockwise. So that's what you send from these output pins. All of the logic to convert that into how the stepper motor moves is done in the motor driver, and then the stepper motor, if you've programmed it and wired it correctly, will respond accordingly. Um, so to give a sense of what this actually looks like, these are just a couple of like traces of channel A, which is the step command, and channel B, which is the directional command. So we've got time on the x-axis, and then we've got voltage on the y-axis. And remember, we're in a digital world, right? So we've only got two choices. It's either 0 volts, which is the low signal, or 5 volts, which is the high signal. So the channel A is the step command. So every time channel A receives one of these pulses, that indicates that it's time for the motor to step. And channel B is the direction. So if you're at the low signal 0 volts, you'll turn clockwise. And if they're high signal 5 volts, you'll turn counterclockwise. And some stepper motors are reversed, so you have to check to see what type of stepper motor yours is. But it's basically, 0 is one direction and 5 is the other direction. And so what will happen in this case is the rate at which the stepper motor turns is a function of how fast you send these pulses, right? So all of the things being equal, this is basically pulse, 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 pause, and then pulse, 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 right? So 3 slow steps and and 3 fast steps. Interesting thing is because halfway through the first pulse, I actually changed the voltage from low to high. So this first step will actually cause the motor to turn clockwise one step. And then I changed the direction to the high signal, and now I'm turning counterclockwise 2 steps. And then I'm going back to the low directional signal, and I'm going 3 pulses, 3 rapid pulses clockwise again, right? So this would actually look like the motor turning slowly one way, slowly back to where it started, slowly one more step in that same direction, and then 3 fast steps back in the clockwise direction. So that's how to read this chart. I should mention before we leave stepper motors that you're not limited with stepper motors like you are with servos in terms of the rotational position. So you can cause a stepper motor to just turn like around and around and around and around, just like a DC motor would without any limitations. You just would put, channel B at 0 volts, right? The low signal, and you just send a series of pulses and the motor will just turn indefinitely. It's not limited mechanically by 360 degrees. Okay, so we have some references here. The slides are shared with you guys. So if you ever need kind of a refresher or a deeper dive into how any of these motor types works, there's information for you there. In the class, we're going to have you guys do as part of your motor laboratory some Arduino simulations. And the real goal here, the software is called Walkwe. It's a browser uh, a browser enabled like Internet of Things kind of platform. And so you can actually grab components like Arduino boards, LEDs, push buttons, stepper motors, servo motors, and so forth, and actually wire them together in this virtual environment and then write Arduino IDE code for them. And then run the code and see if the system works the way that you think it will. So this is actually a great first step in prototyping. No need to actually physically build any hardware. You can build up your hardware essentially in this virtual environment and then write code and see if your hardware functions the way that you expect it to. So for those of you who are like starting to think about, building up the motor control hardware for your prototypes, I would suggest starting like today using Walkwe to build up a system in the virtual environment before you have to build it up in the real environment. We're actually going to do, let me jump ahead here. We're going to do a kind of a motor lab exercise, which is really just me walking around the room, telling each group one at a time how each motor type works. And then to show you like the details of the wiring for each one of those motor types. So you guys will see a demo that kind of looks like this, where stepper motor, DC motor, and servo motor are all kind of described, and how I wire them and how they function is all given in detail. So we'll see that in class. So just to give you a sense of kind of what you need to get started, if you want to, build some of these things yourself. For a DC motor, you obviously need the motor itself. You need a motor controller. You need a 12-volt power supply, and then you need some command logic. So like an Arduino Nano, for example. For um, a a servo motor, there's kind of two different types. So if you're running a high voltage servo motor, you're going to want a 12-volt power supply, a motor driver for the servo, right? Because you've got to kind of mitigate the 12 volts and not send that through your logic circuit. We need some sort of voltage regulator to get from 12 volts to 5 volts, and then we need the logic board itself, and then of course we need the servo. So this is one configuration. If you're running a high voltage servo, more often than not, we run low voltage servos, so 5-volt servos. These can be run directly off of the pins on your logic board. So this is a much simpler arrangement where it's just logic board, servo, and then power supply. And then for a stepper motor, you need the logic, you need the motor driver, you obviously need the stepper motor itself, you need a 12-volt power supply to run the stepper motor, and then you need some sort of voltage regulator, voltage converter to turn the 12 volts from the power supply into 5 volts to run your logic chip. So, okay. We've already seen this picture. This is the demo that you guys are going to get. I've got a schematic here just for kind of reference purposes for you to see how to wire a stepper motor. It's a little bit involved, so I thought it would be helpful to give you a schematic. And then this is a code for the stepper motor that we have in the demo in the class, just to sort of get you started with how to code the stepper motors. So that brings us to the end of the Motor Control Lab lecture. So appreciate your time and look forward to seeing you in class. Thanks.